A production system can process thousands of transactions a second without a drop in performance, until a single piece of malformed data causes the entire pipeline to freeze and crash. Writing code that simply compiles is the absolute minimum requirement for software development. Production-grade Java demands two active responsibilities. You have to strictly optimize the application's memory footprint, and you must build rigorous mechanisms to handle inevitable system failures. An application survives a live environment only when you stop passively reacting to data and start architecting defensive layers. That defense begins deep in the heap memory and extends all the way to the user interface. Strings are the most heavily utilized data type in Java. To prevent severe system bloat from millions of text objects, the Java virtual machine designates a specialized subregion in the heap memory called the string pool. When you declare a string literal, like the word cat, Java searches this pool. If cat already exists, the JVM doesn't allocate new memory. It simply makes your new variable point to the exact same reference node. This process is called interning. Sharing references is only safe because strings in Java are strictly immutable. Once created, their values cannot be changed, meaning one variable cannot accidentally corrupt the data being read by another. But if you declare a string using the explicit new keyword, you override this efficiency. The JVM bypasses the pool and forces the creation of a completely redundant copy of cat out in the general heap space. Utilizing the string pool drastically reduces the total number of objects taking up space in memory. That lowers the active footprint of your application and reduces the heavy computational overhead required for the garbage collector to clean up duplicated data. Memory optimization handles internal efficiency, but stability is immediately threatened the moment an application accepts external user input. Standard console-based inputs like Java's scanner class leave the system vulnerable. They provide a blank text prompt, leaving the user to guess the format and inevitably submit logic-breaking errors, like typing letters instead of numbers. To secure this boundary, you can utilize the graphical components of the Java Swing package, specifically the JOptionDialog class. A method like showOptionDialog completely eliminates free text entry. Instead of typing an answer, the user's input vector is constrained to an array of predefined valid objects, rendered as discrete push buttons. Moving away from open text consoles to tightly controlled UI components cuts off malformed data before it ever reaches your application logic. Even with heavily constrained input vectors, unpredictable state changes, like a missing file or a dropped network connection, will still occur. This hierarchy diagram maps out how Java categorizes application states. Every possible failure state is a subclass of the base throwable object. The hierarchy splits into two main branches. The error branch defines critical system failures, like the JVM running completely out of memory. Developers should never attempt to catch or write recovery logic for these unrecoverable events. The exception branch, however, represents the application-level anomalies that you are explicitly responsible for managing. These are further divided into checked and unchecked exceptions.
Checked exceptions represent anticipated problems, like a missing external file, which the compiler forces you to handle before the code will even run. Unchecked exceptions represent underlying logic flaws that trigger during execution. By separating failures into this rigid structure, the language forces developers to delineate exactly which issues require immediate system shutdown and which can be intercepted and resolved. When an unchecked exception is triggered, it creates a disruptive object that halts normal execution and begins traveling through the system. This call stack diagram illustrates what happens next. The JVM immediately searches the call stack backward, looking for a matching exception handler to intercept the error. If the method where the error originated doesn't have a handler, the exception cascades upward. It exits that method and drops into the higher-level method that called it, continuing this pattern up the chain. If the exception propagates all the way up through the main method without being caught, it hits the JVM itself. The JVM's default response is to terminate the thread and crash the program, spitting out the resulting stack trace. To prevent this cascade, Java provides a rigid containment architecture, the try-catch-finally block. You wrap vulnerable logic inside a try container, which feeds into a catch filter and terminates at a finally exit. The first rule of this containment strategy is to target the most specific subclass of exception possible.
Catching an exact error, like input mismatch exception, gives you a precise diagnosis of the failure, rather than catching a generic exception class that obscures the root cause. Once caught, you must never leave a catch block empty. Swallowing an error silently destroys the forensic evidence needed for debugging. The exception must be fed into a proper logging framework like SLF4J to record the failure state. The containment vessel ends with the finally block. The code inside this block is guaranteed to run whether an exception was triggered or not. This makes it the mandatory location for cleanly closing file readers, network connections, and releasing held memory. A complete try-catch-finally architecture guarantees that even when internal logic fails, the system fails predictably, records its forensic cause, and seals its memory connections. Robust code is proactive. It does not passively await execution. It actively manages and defends its operational environment. The baseline defense is internal efficiency. By understanding how the JVM handles object allocation and leveraging the string pool, you reduce the active memory footprint and garbage collection overhead. The perimeter defense controls user behavior. By replacing brittle console inputs with rigid graphical interfaces like JOption pane, you physically prevent malformed data from entering the logic stream.
The internal defense intercepts runtime chaos. By mapping potential failures against the throwable hierarchy, you can construct specific try-catch-finally blocks that contain cascading errors before they hit the JVM call stack. Mastering these three domains, memory efficiency, input boundary control, and state containment, is what elevates a developer's mindset from simply passing syntax checks to engineering software architectures built for survival.